Hello, everybody, and welcome. My name is Michele, and in this series of lectures, I would like to speak about some techniques and methods that are widely used in physics. I will start saying that whatever I do, it's whatever cross my mind. I'm not following any notes or whatever. It's just what comes out from my mind at the moment. So if there are some mistakes, some errors, something, it's okay. I will correct it. But this is the way in which I do all my videos. I do not like to remake the video or correcting when I'm saying something wrong. It's not the spirit. I just go all in. Whatever it goes, it goes. And also for the aspect of math and general the use of physical formula and equations, I will go all in. This is not a video in which I will explain, as to say, in a more convenient way for the viewers. I will try to do my best to explain it in the way it is, not try to simplify it or making it more digestible. It's going to be just straight physics. If I need to do an equation, derivative, integral, I will do it. I will not skip it, and because the way this is the way which this video will be exposed. So I'm planning on making like 3 or 4 videos. I don't know yet. I don't have any plan. Roughly, I would like to speak about vacuum, because vacuum technology is somewhat one of the most fundamental things that there is for an experimentalist. I'm not myself an experimentalist. I'm a theoretical guy. I prefer theory, but somehow I do believe that having something related to the experiment is a as baggage of knowledge in every physicist's career is somewhat more useful than just delving deeper into the theory without knowing anything about experiment. So vacuum is pretty much present everywhere whenever one needs to do experiments, and the reason is, of course, that we will try to avoid at our best knowledge to have interference with the gases which are maybe contained in a container like this. The gases that it's inside means atom, molecules, ions, which may interact with our sample, with our experiment. And that's why we generally consider to remove this vacuum. And the way in which we would like to remove this vacuum is through pumping, because pumping is effectively the way in which we can remove the gases inside. So pumping out the gases is pumping out is what we want. But I will go through some physical insight about this. So if you would like to stick around and see what we have to say, we will be covering the main topic, even though we will be keeping a very, very light approach. I will not go into the details too much about the vacuum technology, which is, of course, a huge topic. This is just a brief introduction. So if somebody is interested to go into some specific topic, please let me know and we can do it. But in general, I will stay at a very high level without going too much into details. Okay? So, with that being said, I would like to start discussing about the gas itself, which is these ions and molecules which are inside the container, and of course, they will be moving around the container in absolutely random manner. Okay, so they will be colliding between themselves. They will do scattering, and as well they will collide with the barrier, the container, the volume which is encapsulating the gas. And so this is the pretty much the activities that is going around, and it's an important features that we need to consider, that is every particle, every one of these molecule or atoms, they have a velocity, right? And what's it's important for us is to have a function that describe this distribution of the velocities, right? So this function is well known since many times ago, and it's somebody call it Maxwell and Boltzmann distribution. And we can think about the mass over 2 pi kBt elevated to the 3 power 2 e to the minus mv squared over 2 kBt, right? So this is an explicit way of seeing this Maxwell-Boltzmann distribution, okay? So where, of course, I denoted by kBt the constant, the Maxwell-Boltzmann, Stephen Boltzmann constant. T is the temperature, m is the mass, v is the speed. I generally denote like this with it's like a bolded. Instead of making arrows, I don't like making arrows in the vectors. I prefer to use bolded, like you're reading a book. I don't fancy at all the use of arrows or symbols, weird, so I will try to avoid in my video. So if something is not clear, just let me know, but this is the convention that I use. And of course, if one wants to see what will be the distribution of the velocity of these particles that are inside our container, this one, okay, our molecule, and one wants to see what will be the distribution of the velocity, okay, so in the x-axis we have the velocity, and in the y-axis the distribution. We will look at experimentally, and we will see that the type of distribution will be something like this, maybe. Okay. And this is, of course, related to a specific temperature, let's say T equal to T prime. But if we increase the temperature, so if in the same container we will put some heat, okay, so we will have some heating up coming from here, so we increase the temperature. What will happen is that we will have a different distribution. In particular, we will have higher speed, okay, because this is related to the kinetic energy. I'm sorry, I will use this tool, which is much more easier for me. So this will be like the behavior with a T2, okay, T second, when T second is greater than T prime, okay? So if the temperature increases, of course, we have higher speeds. Okay, so one important thing about this is about, let's focus on the blue line first. It's about what we call the most probable speed, okay? Because this is somewhat related to the probability of the speed. Imagine that it's not an individual event. There is a lot of scattering between the atoms with other atoms, or atom with the container. So there is a lot going on. And in this case, the most probable speed will be the peak of this curve. And if we want to see this most probable speed, we can think about as 2 kBt over m. Okay, so this will be the average, as to say, most probable speed. Whereas if one wants to calculate what would be instead the average speed, for example, the average speed, surprisingly or not, it will be, let's say, mean speed. It will be an integral from 0 to plus infinity of this distribution f of v times v in dv. And this appears to be something which is slightly higher than the most probable speed. So it's something that goes over kbt over m for sure, and there is a pi and a 8, right? So it's roughly a little bit bigger, because if you think that in here you have like 8 divided by 3 roughly, so pi 3, 4, 14, 15, so it's 9, 5, 3, 5, blah, blah, blah. Is that right? I'm not sure about this. 14, 15. Okay, I don't remember pi, but it's fine. This is correct, by the way. This one is for sure like this. But in any case, this is roughly 3. 8 divided by 3 is definitely a little bit higher than 2. Okay, so we will see something crazy here, because the mean speed, okay, is a little bit bigger, okay, than the average speed, the most probable speed, sorry. So the most probable speed will be this one, whereas the mean speed will be the red one, so a little bit higher. And okay, so this is very nice. Now we have a clear understanding of what's going on in a container. We have understanding of what's happening to the velocity, the distribution, how it is distributed according to the temperature, so on and so forth. But at the end of the day, we need to deal with vacuum, and vacuum is related to the pressure. But what is actually in physical terms the pressure? Well, in a physical sense, the pressure is just the quantity, okay, of this molecule bouncing on arriving on a specific surface. So we will introduce a quantity which is we call arrival rate. Right? The arrival rate is defined as the number of particles, molecules, whatever, that arrive into a specific surface. This can be the S, this surface, this one, at a given time. Okay? And this is the quantity that is related to the pressure. Okay? So the arrival rate is proportional to the pressure. Okay? So it's somehow discipline what will be the pressure like into our container. So the amount of particle that are keep hitting the surface, okay, the surface that we are considering. The more, the higher the pressure, of course. So in this regard, this relation between the arrival rate and the pressure, okay, so we can think about the arrival rate as the pressure divided by 2 pi m kbt. Okay, somehow this is the way in which it's defined, but you can say that this arrival rate is proportional to the pressure. So the higher the pressure, the higher the arrival rate, and likewise, the lower the pressure, the lower the arrival rate. With all the other parameters considered as a constant. Oh yes, pi is 14, 15, 9, 2, 6, 5, 3, 5, 7, 8, 89. No, probably 79. Probably 79, 89. Now I think I got it right. Yeah, yeah, should be okay. Let's move on. Another topic which is important, very important, is about the mean free path. Okay, the mean free path is the distance traveled between two scattering events, right? So if we imagine that we have an atom here and another one here, and a particle that is scattering, okay? So it's scattering here and then it's scattering again here. So we will call this distance lambda or mean free path. So it's the distance between two scattering events. You can imagine that in a very crowded environment like the container with full of gases, there will be a lot of scattering event, a lot of collisions. So the mean free path will be shorter if there is a lot of particles, and of course, on the contrary, it will be longer if we have less particles into the container. So somehow we see even just by thinking that this mean free path has to be proportional to the inverse of the pressure. So as I said, if we say that the pressure is going up, then the lambda is going down, of course, and if the pressure is going down, the lambda is going up. So lower the pressure, the higher the mean free path. Okay, so we discussed about the mean free path, we discussed about the arrival rate, and so maybe it's time to introduce some of the particular things that are used in vacuum technology, because at the end of the day, we have to remove the gases inside. We have understanding of the speed, we have understanding of the pressure, but now we need to take this off. And in order to take this off, physicists consider a quantity which is called throughput. Okay, which is considered as a flux of matter, a flux of particles that is released by a container. And it is done by considering the pressure constant, so it's P dV divided by dt. Okay, so it's the pressure times the derivative of the volume with respect of time, or the time change of rate of the volume. This is the definition of the throughput, which allows us to kind of consider our important parameters, because when we evacuate from a container the gases, we actually need physically a pipe. Otherwise, it cannot be done. So, but a pipe, which I'm sure that everybody is familiar with, needs to be connected to our pump, and therefore we know from fluid dynamics that there are some important physical parameters related to the pipes, in particular the conductance. And the conductance, let me write it better. So the conductance is defined as the ratio between the throughput and the delta P, the difference of the pressure that one has. Likewise, we can introduce another parameter, which is impedance, and which is, roughly speaking, just C to the minus 1. Z is C to the minus 1, the inverse of the conductance. And we have a different behavior according to how the pipes are arranged. For example, if we have, let's say, a series, what is called a series of pipes, we have a situation in which we have a pipe with some big diameter, let's call it D1, with a certain C1 and Q1 conductance and throughput, and it goes into a smaller pipe like this, okay, and in this case we have let's say D2, which has conductance to Q2. So in these cases, if we want to calculate the total conductance, so we call it total, we may have more than 2, we can have 3 or 4 or whatever number. The point is that the total equivalent conductance will be the inverse of the sum from 1 to n of the individual Ci, okay, each pipe. So if we do this summation here for each of the one, in my example just 2, so it's 1 over C1 plus 1 over C2, and I make everything the inverse of that, I will find the total conductance. And of course the total impedance, it will be just the sum, okay, of Zi, okay, from 1 to n. The other way of arranging pipes, instead of by series, it's in parallel. Let me give you an example, but first let me state this is series, and in parallel will be something that we can, the pictures in our mind in this way, okay? So we have 2 pipes, which becomes one. So we have like diameter 1, of course with C1, Q1, and we have here D2, which may be equal or different, doesn't matter, okay? But in reality, at the end, we have a D3, C3, Q3. So the flux will go from this pipe, from this other pipe, and will converge in here. So when this occurs, we have the inverse situation. In fact, if we want to calculate the conductance, will be the sum of the individual conductance, so the Ci, and the impedance will be the inverse of the sum, okay, in this way. So parallel and conduction. Okay, so now that we have somewhat of a vague understanding of the how this parameter works, what is the throughput, the conduction impedance, which is related to the pressure in this quantity, this throughput quantity, we can introduce another physical quantity which is essential for us in vacuum technology, which is the pumping speed. Why? Because when we connect our pipe to our pump, and the pump is start pumping out the gases, as we will see, we will achieve different level of vacuum, and I will talk about this in a second. But the important quantity here is the pumping speed, which we can think about the throughput divided by the pressure, okay? So if we have in mind what would be the throughput, which is this quantity which we described, which from a dimensional point of view can be thought as a pressure which is multiplying a volume divided by a certain time, okay? And we take this dimensional analysis in here, okay, which stands for the Q, okay, and we divide it by another P, which is this one, At the end of the day, we find out that the pumping speed from a dimensional perspective is just a volume divided by a certain time. Okay, so the volume evacuated from the container in a specific time is what the pumping speed is measuring. Of course, if we connect it into a pipe like this, we need to consider that there are some losses of the efficiency of our pump, because of the fact that there are localized losses, there are distributed losses, as the fluid dynamics teach us. Then you have the classification, the various type of fluid motion, which are denoted by the Reynolds number. Of course, if there is the Reynolds number is below 2200, then we have laminar flow, intermediate flow. If it's above, it's a turbulent flow, but I won't go into details of this now. What is important for us is that we have our container that we need to remove the gases, and we do it with a pumps, or to be more precise, with a set of pumps. Why with a set of pumps and not with just one pump? This will be clear in a second, but let me give you roughly an idea of what is pressure, because everybody is familiar with atmospheric pressure. And this is 1 atmosphere of which is equal to this quantity in Pascal. If we measure in Pascal, I would like you to remember that Pascal is Newton over square meter. Okay. And we can have a classification of the vacuum. Okay, which goes from let's say a range which is not interesting for us, which is let's say atmospheric, not interesting. We have a medium vacuum and high vacuum and a ultra high vacuum. Sorry. Okay, so, and this is measured into various ways. They are all equivalent, but somehow you will find it into various way. One of the popular way is measuring it in Pascal. So for us, a medium vacuum is what it goes from 100 Pascal to 10 to the minus 1 Pascal. Okay, so this is what we discuss as describe as medium vacuum. Remember, this is the atmospheric, so where you and myself are actually, plus or minus, under 1000, and this is the medium vacuum, so 100 or 0.1. For high vacuum, we mean something that goes from 10 to the minus 1 to 10 to the minus 5, okay, Pascal. And for ultra high vacuum, we refer to some vacuum that goes from 10 to the minus 5 to 10 to the minus 10, okay? Is this a very high vacuum, ultra high vacuum? Well, this is what we can achieve in our laboratories. In all the experiment can be, which can be requiring a ultra high vacuum. This is what we can achieve. But is this a good vacuum? Well, here on Earth, yes, the most good vacuum that we have is, of course, in the outer space, is not in the solar system, because in the solar system there are still a lot of a lot. There are still some something, okay, but into the intergalactic vacuum, then we will have the lowest possible vacuum, which is like 1 proton per cubic meter. We have 1 or 2 proton per cubic meter. That's the most advanced, as to say, vacuum which is possible. But here we have a very, very different vacuum with still order of magnitudes of particles into per cubic meter. So we even if we call it ultra high vacuum, is related to something technologically achievable here on Earth. Okay, but it's not nothing related to the outer space. But going back to us, without digressing too much, it will be also useful for you to have in mind a different units, which can be, for example, the millibar. Millibar is pretty much used, and it's fairly simple. We just need to divide by 100. So whenever we have 100, we have 1, or 10 to the minus 3, and here 10 to the minus 3, 10 to the minus 7, 10 to the minus 7, and 10 to the minus 12. Or again, we can have another way of technical way of measuring pressure. We can be the torr. With the torr, we have to consider the 760 millimeter of hydrogen as atmospheric pressure. Therefore, with the correct convention, we have 0.75, 10 to the minus 4. We have 10 to the minus 0.75, 10 to the minus 4, until 0.75, 10 to the minus 8, 0.75, 10 to the minus 8, until 0.75, 10 to the minus 13. Okay, so this is the classification of the different type of vacuums that we have. I was saying something about, then I interrupted, about the way in which the pumping speed is affected by the use of pipes. In particular, this is the relation which is important, which is the effective pumping speed is 1 over S plus 1 over C. Okay, where of course this is the conductance, which depends on the type of pipes. Okay, so we have discussed the type of vacuum, we have discussed the pumping speed, or maybe we can see what is the most important equation in pumping technology, which is this one. It's minus dP over dt, which is equal to Ps minus Q. Okay, so this is the equation that we need the most when we are dealing with the pumping of gases from a container. And the reason is that this has two regimes or limits. Let's call it short limit and say short time limit. Short time limit, and we will see later the long time limit. For the short time limit, what we need to consider is that we have our container, as shown here, which is connected to a pump, okay, with a small pipe, and let me picture the pump as this cross, and the pump is pumping out the gases. So we are effectively reducing the quantity of gases inside. And since the volume of this container is known, for example, we have this volume V, and we have the pumping speed here, it should be fairly simple to evaluate okay, the time that it takes to reach a condition in which the Q is equal to 0, all right? So whenever we have Q equal to 0, we have finished pumping in the short time limit, of course. And therefore, we have minus V dP dt, which is equal to PS, okay? The pressure times the pumping speed, because Q is equal to 0. But this is a simple differential equation in which we can separate the variables. In particular, I will take the P on one side and the other variables on the other side. So let me say which is minus S divided by V dt, okay? Now, if we integrate this equation here, both sides, we will get the integral of 1 over p, or 1 over x. If you remember, the integral of 1 over x is just the logarithm of the modulus of p, evaluated at p and p naught. Okay? And whereas on the other side, we have minus s over v t. Okay? And what we have here is that we can find a relation between our logarithm. Evaluating this would be p divided p naught is equal to minus s over v times t. So if we pass to the logarithm, we have that e to the, which is a natural logarithm, so it's going to be e to the minus s over v times t equal to p over p naught, or p, the pressure, is equal to p naught, the starting pressure, e to the minus s over v times t. So this is the final pressure that we can achieve after with that pumping speed of that volume at a certain time. So we can calculate what would be the final pressure starting from a P naught pressure and knowing the pumping speed, which is something related to the pump itself, the volume that we know of the container, or we can calculate, or we know from the beginning, and the time that it takes to reach that pressure. So this is for the short time limit. But the point is, the whole point of vacuum technology is that I want to introduce this because before going to the other limit, is that no, I will tell you later why. Let me conclude instead with the long time limit. In the long time limit, which is simple, long time limit, so we keep pumping. We have reached a condition in which our pressure does not diminish further, even if we keep pumping. So we have pumped for days, okay, and the pressure does not drop at all. This means that if you go back to the main equation, this one here, let me take it down for a second. It means that we have reached a situation in which the pressure itself does not vary any longer with time. So it becomes a constant, okay? But if it's becoming a constant, its derivative is equal to 0. And therefore, we can greatly simplify this equation just by stating that Ps minus Q is equal to 0. So we have an ultimate pressure, which is essentially just the throughput divided by this pumping speed. So this is the long time limit. Okay, so now I want to introduce to you a concept that you might not be familiar with, because so far we just have a discussion about physical mechanisms, some fluid dynamics, and nothing more. But if it was just for that, it will be fairly simple to pump out the gases from a container. We just connect to the pump, we switch on our pump, and the pump is removing all the gases. Okay, so we have our container, which is completely evacuated and there is not a single atom inside. Is it so? Not at all, because if it were so, we would have finished. It would be very simple. The overall difficulties on pumping technology is that there is gases that are trapped inside the container. In particular, they are trapped into the surface of the container. So if we zoom a lot into here, we zoom it, what we have is our container, which is of course made of atoms. We can even have been cleaned, we can do whatever your heart desire, but at the end of the day, there will be thousands of our atoms which are absorbed by the surface. They are they are kept in a position by some interaction that we will see in a second when we discuss about gas surface interactions, but they are there. As soon as we reduce the pressure here, okay, in this area, they are start to be released, okay, and this increases the pressure. So the overall difficulty of vacuum technology is to remove such phenomena or to reach a condition in which it's mitigated the most possible way, in the most possible way. Plus, it's not that there is just other atoms, molecule or ions encapsulated into the surface. There is also water or some other atoms that are very annoying for if our task is to reduce the pressure. So the overall difficulty of vacuum technology is to remove this outgassing, is try to mitigate it. And so when we calculate the type of leaks, okay, we have a true leak, which can be something that is coming from a connection, or from the pipe or the pump itself, a true leak, or a virtual leak, which is this outgassing. So the gases that is released from the surface inside the container. Why it is released, why it is absorbed in the first place. Then we need to discuss a little bit about the gas and the surface interaction. We have two phenomena, which is absorption and the other one is called desorption. Okay. Absorption itself and desorption will be very much used in these videos. In particular, we will discuss about, not in this video, but in the next one, in which I will speak about the different type of pumps. We will see why absorption plays a role in the pump, whereas desorption is the responsible for outgassing. Okay, but absorption, just to give you an idea, can be divided into physisorption and chemisorption. So the physisorption is the physical process in which the gases are trapped by the surface because of some forces which are related to the van der Waals forces. So if we have a plot of the, let's say, forces as a function of the distance, okay, we have our molecule that is far away is feeling no forces, then there is a behavior like this, first an attraction, then if it's too close, a repulsion. But at the end of the day, the dipole forces are causing this physisorption. So it's a physical process in which atom of the surface and atom of the gases are acting, are exchanging dipoles forces to it. Whereas the chemisorption is a little bit more deeper phenomenon because it involves the exchange of electrons between the parent atom of the surface and the atom of the gases. So there is a behavior of this type. So in here we have the first round. This first trough here is related to the um, physisorption. The second one is to the chemisorption. So as I said, it's related to the exchange of the electrons between, like a chemical reaction is just exchanging electrons between different atoms. In chemisorption is a process in which the gas of this, the atoms of the surface exchange electrons with the atom of the gas of the container. So they are trapped, okay? And as soon as the condition, the pressure inside, the pumping condition have reached a certain value, okay, so the gases that were absorbed on the surface, or water if you like, okay, you can also have a water molecule or other gases, they start to be released. They start to be released, and we need to keep pumping. We need to keep pumping in order to remove this extra outgassing. Okay. If we suddenly stop pumping, the pressure will immediately go up, okay, because of the outgassing, because they are free to be desorbed by the surface and wander inside our container. And this is something that we do not want. So in order to keep the outgassing controlled, it is also important to make a process which physicists, experimental physicists call baking. Essentially, they bring the temperature of everything, pump, container, pipes, baking temperature of, I think, something like 300 Celsius, something like that. They call it that they bake the pump. That's why you will see, if you have seen a pumps or a vacuum technology, you will see all metallic like tools and equipment. It's because of the baking, because they want to bake it so this water that is in contact with the surface of the internal part of the container is released, and by baking and pumping, they will obtain a very good vacuum, a very high vacuum, or even ultra high vacuum. So I would like to close this video now because I'm a little bit tired. In the next one, I would like to speak and go into the details of the different type of pumping. We will see that it's not sufficient to have only one pump that goes from the atmospheric down all the way to ultra high vacuum. We need different pumps, and they are based on the two, as to say, category. One is related to the throughput pumps, in which they remove the molecules from the container itself, and the other one, sorry, that is related to the process of which I was introducing here, chemisorption and physisorption. So thank you very much for watching. I hope I didn't annoy you, and you have learned something, hopefully, and looking forward to see you for the next video. Good night.